So, last time we talked a little bit about inheritance, and I just wanted to do a little bit of review on that, and then show the fix that I found. So last time the program wasn't compiling at all, and that's because there's a feature in C++ that is a little strange, that has to do with inheritance, where if you do inheritance, it doesn't actually inherit naturally unless you put the word public. So if I put the word private, which is there by default if you don't put anything, or protected, it will default every one of these keywords to the strongest version. So if it said private, it will change all of the public variables to private and all of the protected variables to private. And if I set it to protected, it will set all of the public variables to protected. So basically, if you put something more strict than the current modifier, it will change it to that, which is a bit of a strange side effect. I don't quite understand why that's the default behavior. But so in general, I just recommend doing public. If you make public inheritance, it's just going to keep exactly the same keywords that were on all of these, which is, I don't know what I would expect. Yeah, at least a few more people are joining. Put this down here. That's what I would expect, I guess, when I do inheritance. But that's okay. We've got it figured out. So let's just review a little bit on inheritance, and then maybe we'll go over the third assignment. So I put up the third assignment a little bit earlier today, and I set that be due next Saturday. And assignment 2 is due on Saturday, this Saturday. So if you haven't gotten started on it already, I definitely recommend it because it is not super straightforward. Okay, so let's talk a little bit about inheritance again. So we've had this, mini game that we've had going where we have game objects and then we put them in the game and we render them to a screen and we can move them around. And so what we decided on was that perhaps it was a good idea to start creating new classes that were unique for specific objects. So I could have like a player class and an enemy class and item classes and stuff like that, where they do unique things and they have their own unique code, and they only really need access to that, and anything else, the player doesn't need access to things that the enemy has, and vice versa. The enemy doesn't need things that the player has, but they might all need some common things that we've already had in the game object class. I'm holding this upside down. Like ID or updating or stuff like that. So our idea here is that we want a game object class, and we want that to have things that we want everything in the game to have, which would be something like an ID, and we'll start adding some more stuff here. It might be an ID, a character to represent it, so some sort of graphical representation. Just call that print C. And so we want everything to have that, but we want individual classes that borrow from this but have their own specific things. So just to illustrate this, it can have both fields like ID and a print character that are primitive types, integer and character, and it can also have things like functions. So I can have void update, and that's something that all of them do, so every frame they do something. Let me make this a little bit longer. Okay. Something like that. And so our idea is that we want there to be some unique things. So I want perhaps a player, and I want the player to have something like a jump. Excuse me. So the player might have functions that are unique to them, and then also something, like health, and whatever else you want to add later. And the idea is if we have it inherit from this, it will copy all of the stuff that comes from GameObject, and will also, any code executed on GameObject will end up reflecting in the player class, while still adding its own things. And we don't have to copy and paste anything. We don't have to worry about them not sharing anything and having to make static variables or globals or anything like that. And so same thing, we'll do a similar thing with the enemy. So we will maybe give that some sort of function. So I don't really know. Whatever. Something. It might be some sort of behavior like attack. So let's just say void attack. Something that's unique to that specific item. Alternatively, you don't even actually have to put code in it. It could just be totally blank. That might seem a little bit nonsensical, but the reason you might do that is to create a class, because you can actually, I don't know if C++ supports it, but in most languages you can put a, what's it called? The word is, and it will check what type of object the thing is, like what its class is. So I could use that to just check classes if I wanted to make a distinction. I've done that a few times before. It's not the worst way to go about doing things. And then we'll just say item. So this is what we'll work with for now. So we got game object, we got player, enemy, and item, and these are all going to inherit from the game object. So I might have something like void collect for an item. The idea is that all of these will share the same code from GameObject, and that they all have their own unique stuff that distinguishes them from the other things. I still want to make that M a little nicer. And then, like we were saying before, we can keep inheriting. So I could say, oh, I want a key item. Maybe I want a sword and stuff like that. So if I need to keep going out and being more and more unique with my actual classes, I can keep inheriting and keep going as long as I want. And in fact, I could do some other crazy stuff that we probably won't get into, like inheriting from multiple of these, or doing things that can't be instantiated at all with abstract classes, which I don't think is a keyword you can use in C++. It's more of just a concept, but other languages have it. Okay, so I'm going to close that. Right, so is everybody okay with that? Just a refresher on what inheritance is. And I think we did another example last time where we talked about animals. The idea that, I guess logically, if you're thinking about these, each of the things below it are examples of things above it. So a player is a game object, an enemy is a game object, an item is a game object. But the other way around is not necessarily true. Like a game object doesn't have to be a player, or an enemy, or an item. Right, so if we go back to the actual code that we were working on, we started last time to create a player class that inherits from game objects. So remember that the way you do inheritance is with the little colon. And what I was saying for everybody who's just joining is that we need the word public in front of this. So that's why it wasn't compiling last time. If you don't put the word public, it will default to private, and it will change all of these modifiers to private. So all the public variables in the base class end up becoming private in the inherited class, which is a little bit strange. I don't know why they did that, but that's the way it works apparently. So just make sure you're putting public in general. I think that's the most common sense kind of implementation, is to just keep the modifiers from the base class the same in the derived class. And I guess I will start using those words. So base just means it's a parent of it in this tree that I drew. So this would be a base class, and the ones below it would be inherited. So let's just write that out really quick. So this is a base class, and these are all inherited down here. So we got that. Right, so what we did here is we created a player class and we gave it the ability to jump. And what I'm going to do is just go here and copy. I already wrote code for jump from the first part. So I had something like this. So let's just copy and paste that, or cut and paste it here. And I don't need a object reference anymore because I'm talking about the actual object. Alright, so jump, that just moves it up to, so I know I didn't actually show the implementation, but add to position just adds this many x coordinates and that many y coordinates to whatever object we're dealing with. So this one will move it 0 left and right and 2 up and down, which kind of makes sense for a jump in our 2D game. And I will say when the controls are jump, we'll do player.jump. And then I just had that poured down, but maybe it's a good idea to put a break. Okay. And so maybe we'll do the same thing with the enemy here. So we had an enemy class. So let's go ahead and make a drive class for that. And yeah, let me actually, really quick, what we can actually do just to make things more convenient is I'm going to change this constructor here. So we always want the player to be P. So let's change the constructor so that it always puts P. We don't ever have to type that in. And then I'm basically just going to do the same thing on enemy. Enemy class. Right, so again, we just do a normal, whoa. You want to type the name in, right, and actually have your hands on the right keys. We'll create an enemy class, and it will also inherit from game object. So enemy will also be an example of game object. We don't want it to have the ability to jump. And we'll give it a constructor similar to the player that just takes a position, and that's it. And then updates the position to be that position and as an enemy. E. Okay, so now I can declare this one instead of a game object to be an enemy and just give it a position, and it will automatically do the E part. And yeah, we'll roll from there. So hopefully it should pull open a terminal soon. There we go. Right, so it still reads the fact that there are two game objects. So remember from our code that we had a static variable called count somewhere. Oh, it's private. We had a static variable called count. And that was something that everything could see, right? And that incremented whenever we generated an ID, which happens whenever we create an object. So you'll see here it generates an ID in the default constructor. And then in the player and enemy, we also said generate ID. So that gives them their own unique ID and adds to the count. So even though I didn't create any game objects, I created a player and an enemy. When they inherit it from it, they still call the same code. So if I was to try to play the game now, you'll see it works the same as it did before. And it picked up on the E and the P, and now these are their own separate classes. And just to demonstrate that, let's take a quick look. What does protected mean and its difference to private? Okay, good question. Yeah, so protected means that any of the base classes can access it, and private means that only the class itself can access it. So if I look at what I made protected and private, I generally make things protected, just because I think it makes more sense. But I have private here move in bounds. So if I was to go to the constructor, let's just say, of the player and type in move in bounds, you'll see it should give me an error. Yeah. And the reason it gives me an error there is this is a private variable. It has a private modifier on it. That means that I can only access it within the game object class, but not within any other outside functions like main, and also not within any sort of inherited classes like the player or the enemy. So player is not allowed to access any sort of private variables from the class that it actually inherits from. But you'll notice something like print character, that was actually protected. And protected means that it's not accessible outside of the class, similar to private, but I do allow it to be used in any derived classes. So here, player is able to access print character because it's protected. But if I was to go into main and try to do something here, like say enemy.print car equals D or something like that, it'll give me an error and tell me that's inaccessible because it's protected. So it's basically just if you want to have the advantage of keeping it hidden like private, but you want to be able to use it in the derived classes, you want to use protected. Does that answer your question? Make sense? Okay, awesome. Okay, let me make sure nobody's trying to get in. Okay. I guess we just don't have the biggest class today. Who knows? Okay. Yeah, so that's a general overview of that, and then I just want to take a little bit of time to talk about how we can use this to do some good object-oriented programming. So, let's talk about a few things here. We'll kill two birds with one stone. I'll talk about some good programming practices as well as some efficiency here. So I want to update every single game object that I have in my game. And so I've created player, enemy, and I could create more. But with the way I currently have it set up, I have to actually physically update them and then add them to the screen. And I think that's kind of obnoxious. Because if I keep adding more objects, I'm going to have to keep writing 2 lines of code each time, one update, one add object to screen. And if I get more and more things that I want them to do every single frame, then, there's going to be a bit of an issue. So, let's try to mitigate that a little bit. So first off, I'm going to take this add object to screen. Here, this takes the screen, and then the clear screen, and the print screen, and all of this stuff. I am going to copy and paste all of this, and I'm going to make them public functions. So let's go down here a little bit. So I'm going to add these right in here. I'm just going to do these as declarations. And the other thing I'm going to do is I'm going to make these all static. 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 Actually, I'm not going to make this one static. I'm going to change it. So I'm going to make this static void add object to screen. I'm going to make that one not static. So what I'm doing here is I'm moving all of the variables associated with printing the game objects to the screen to the main class. That way they're all located in one convenient location. Right, and then the reason I can delete this one if I make it not static is I want to add an object to the screen, and I was previously copying the game object given, but if I apply this to a game object itself, then it will add that specific object that I'm calling it with. So let's really quick add all of this stuff. So remember, in order to implement outside of a class, that we need to put the name of the class that we're implementing for and then the scope resolution operator. So this one shouldn't match. And in fact, I might have to put static. Ah, there we go. No, I don't. Right, so now you'll notice if I delete object, it's totally okay with that because it knows I'm talking about the object that I'm calling it with. I'm going to do this really quick, and it's probably going to look a little strange. But if I put star this, it will mean the object that's calling it. We don't have to worry about too much what that means right now. We'll get into it next week. But for now, let's just say that's going to fix it. Okay, so if we run this again, we should get a compiler error. That's probably because I didn't write enough stuff. What exactly is the issue? External conflict, clear screen. Is it because I didn't put static in front of these? Symbol void add object to screen. Oh no, I'm calling it with the wrong amount of parameters. I wish it would say that. Oh, and I also have this. So I move these to game object. Ah, yes. These are static now. So remember the way we call static, again, is just with the scope resolution operator. Although you can use an instance, but I'd rather not. Okay, so let's just make sure this actually works first. Ah, right, I changed this to be not static. So now, yeah, what I guess I was saying earlier is if I make it non-static, I can do something like player.addObject to the screen, and it will now add the player without me having to give this second argument. It will just automatically know, oh, it's that object because it's the one I called it with. So now if I run it, it should hopefully work. Seems to be running. Cool. And again, it seems to work fine. Okay. So that's nothing new having to do with inheritance, but we've basically shown that it's very convenient to move things to the same class that they're in. And I guess the point I was trying to get at here was that this part of code is kind of annoying, having to call update every single time and add object to screen. So here, let's talk about, well, actually, first things first. Let's do this outside of the class, and then we'll optimize it a little bit later. So I've created in advance a vector called GameObject. And we'll deal with that in a second. Let's do a example here. So let's say I create a game object called GameObj. So it's just some arbitrary game object. And I'm going to comment this out so you can't see the answer. But I'm going to write 2 lines of code here. And this. Maybe I should move that a little bit down so it would be valid if I uncomment it. So let's just say I create a new game object and I decide I want to set it equal to the player or do player equals game object. Now one of these lines of code is actually valid and the other one is going to cause a compiler error. At least inherently. I can fix it. So out of these, we know player is a derived class from GameObject, and then GameObject is a base class of player. Any guesses as to which one of these is going to work? And if so, why? So do you think I can set a derived equal to a base, or a base equal to a derived? And I can pull open the diagram if it helps. So if I look at this, would we be able to go that way or that way? I'm guessing the first one because GameObject doesn't have all the things the player has. Awesome, yeah, you got it. That's right. So what he or she is saying is that yeah, I can set a player equal to a game object, and you'll notice if I uncomment this, you're exactly right. I can set a player equal to a game object, but a game object I can't set equal to a player because a player has all of the things that a game object has, but vice versa is not true. So consider that the player has extra things like jump and health and all that. So when I try to set a game object that doesn't have things like that, it's not going to work. But if I try to do the other way around, it totally is. So here with this diagram, you'll see a player is going to have ID and print character and update and jump and health. And so a player is going to have all the things that a game object has plus more. So it's totally fine for me to do game object equals player because it's basically just a game object with extra things. So this is totally allowed. but the other way around is not. Although you can make it work if you do a cast. So if I put player in front of this in parentheses, it would work. Although you might get some errors if you try to access the data that's not actually there. Right. Okay. So does that make sense? And another way, again, to think of it is if the is-a relationship works, then you should be able to set it equal to. So a player is a game object, so I should be able to set a player to a game object. But a game object is not a player, so I shouldn't be able to set it equal to that. Any questions on that part so far? Okay. If you have any questions on it, just let me know, because it might be a little abstract, but you trust me that it does work, and it's very common in practice to use that. So what I've done here is I've created a vector of game objects to store all of my objects. All of the game objects. And so the reason why we went over that is because you'll see now if I try to do something like objects dot pushback player, that it should work, because a player is an example of a game object. So it will say that's fine because a player is a game object. I can add it to a list of game objects. And then same thing if I was to do that with enemy, that will also work because an enemy is an example of a game object. So we'll take it. And so that's great now because instead of doing this stuff every single frame, right, so the reason I moved these over, let me remove this altogether, was let's just say in the update function, we will go, where did I put it? Somewhere in here, right? I will also add object to screen. And then let's just move this down so it knows about it. Ah, yes. I will need to do something else. It requires a screen as well, right? So let's take this screen. And what I'm going to do is I'm going to move the screen. And you'll notice now everything that has to do with the screen is within the class. So this is a good example of something that I'd want to be private. Right, so I can have a static screen. User doesn't have to know anything about it, doesn't even have to know its existence. We handle all of the stuff that has to do with it inside this class. Cool. And then I will... Well, actually, I guess if these are static now, I don't really even need that anymore, right? It already knows what the screen is. It belongs to the class. Now these are down to 0 arguments. I started with 2. It's a little bit helpful. So there's that. Don't need an argument anymore. I can clear the screen. I can print the screen. Just need to change these a little bit. And again, it will already know what screen is because it's a member of the game object class. So it will recognize the variable screen because it belongs to the game object class, which is what I'm writing this code for. Well, so actually, let's just make sure that works really quick. Well, it probably doesn't because did I delete the update? I haven't yet. So it should work. No, it doesn't. What's wrong? Private static class game object. Screen 9. Unresolved external symbol. Private static class game object. Did I not fix all of these? I think I did, right? Perhaps it needs it to be a global. That'd be a little bit strange. I can't put static on that anymore. Does that fix it? No. Question is, why is it not taking that? I might just have to move it back for the time being, but this is ideally where we want it to be. Unresolved external. External symbol. I don't really know what's up with that. Oh well, let's just move it back for now. I guess we're not going to go super efficient then. So let's add the screen back, all of those, and then add it back up the top. Okay, that's alright. Just make sure it compiles. No. Yeah, okay, whatever. I think what we're going to do is we're just going to pass the screen to this just to make it easy. And then we'll do that, and then we'll fix the update function. Okay, well, that's alright. We've still at least cleaned it up a little bit. So now we have to update these with the screen. And what we were doing, or the reason we were doing this, is we were saying, oh, we're going to store all of these game objects into a vector called game objects, and now I don't have to individually call update every single time. I can just call it on everything in the vector. So I can do something like for int I equals 0, I less than objects dot size, I plus plus. And then I can update each individual object's sub I dot update screen. And so now my code is a little bit more convenient. And again, it should work. Up, up. Although that's a little strange. The controls are no longer working. I seem to have broken everything. I did add these, right? I'm clearly doing something wrong. Let me just... If this says 0, I'm just going to go back and... We'll just drop it and come back to it at a different time. So it's obviously creating them. Size equals 2, yeah. Maybe I'm just not rendering the screen anymore. I'm not too sure why it's not updating the controls anymore. I don't think we're going to bother fixing that bug. I might fix it before I put it on canvas at least. But I'm not too sure why that's happening. Oh well. Hopefully at least the point is still clear. I have no idea why that's not updating though. It's really strange. Okay, well. So be it. We have a game that doesn't work, but at least it looks clean. Does all that make sense though? The idea of now we can, with inheritance, be able to upcast objects to match their parent. So I can create a list of game objects that's just all entirely different types of game objects that inherit from it, and kind of store them all in the same place. And so if I ever was like unsure of what exactly I'm going to receive, whether it be like a player or an enemy or an item, but I know it's a game object, I can create a variable of that type, and it's fine for me to just upcast it. And assign it to something that's higher on that inheritance tree is totally fine. Okay. So if nobody has any questions on that, I guess I'll end up fixing this and putting it on canvas later. let me just briefly go over assignment 3, which is already up, and it'll be due next week on Saturday. So we have an assignment here, coincidentally also about video games. I didn't write this one, but I guess somebody else was thinking the same thing I was. That has to do with inherited classes. So we have 3 player classes and 4 weapons. So this will be your first assignment where you have multiple files. So we're going to have a main.cpp and then 2 header files. Each has to do with the player and the weapons. And just remember, again, if we want to include header files, you just got to put that at the top of your .cpp and put include, and then the name of the header file you want. So when you go to compile this, you just want to compile main.cpp, and the fact that you include it will automatically put these 2 files into your compilation. So essentially we're just going to have a player class and a weapon class, and then we're going to inherit them. So we're going to create a base player class that contains all the information that a player needs, and then 3 inherited classes, a red class, a blue class, and a green class, and they'll all have each unique things, probably the weapon, if anything, as you can kind of see there, and potentially some other stuff. Right, so we have a name as well. And then, again, we're going to do the same thing with the weapons. We're going to create a weapon class and then inherit from it to make 3 different types of classes there. And then the rest of this, I think, is pretty decently explained, so I'm not going to go into as much depth as the last one in the interest of saving your time. Any questions on that one either? Okay, it's on Canvas, so if you want to read all the specific details, it is there. Okay, I don't see any questions, but again, if at any point there's anything you have questions on, just stop me. I think that's everything I wanted to cover regarding inheritance and static variables and like how we can be useful with that, or make it nice to read at least. Okay, so let's start talking about some things that aren't strictly programming related. Okay, let me find my pen. Alright, so let's get technical here for a second. Gonna open that up. So when we deal with variables, or any data, including programs themselves, like the instructions that have to do with programs, you kind of hear about binary pretty frequently. So obviously these need to be stored in some way, and that's binary, where we just store it as some amount of bits and bytes, and just magic happens, right? So maybe we want to be able to actually deal with something low level like that, where we can look at the bytes themselves and do stuff, or at least access specific parts of memory. So whenever I say memory from now on, I'm going to be referring to RAM, but it could be different types of memory depending on the scenario. Okay. So yeah, so let's say we have a space of memory. This is just RAM. So whenever I do something like int x, some program I'm writing, the compiler has to turn this into something that the computer actually understands. And it needs to interface with the computer and deal with the fact that it's an actual machine that has all of these unique parts to it. So when I do something like int x, what the compiler is going to have to do is it's going to go into memory, and it's going to say, I need to find space to put that thing, since all variables really need to take up space. So there's two aspects that we need to worry about. We need to worry about the size of the actual object, how much space does it take up, and then we also need to find a place to actually store it, right? So I'm just going to label these conveniently 0, 1, 2, 3, 4, 5. That's it. So 0 is the top of this one, 1's the top of that one, 2's the top of that one, 3 would be this block, 4 would be that block, 5 would be that block. So I might have something here where I say, well, integer x, I'm going to put that at 0 because that's open. And maybe there's different criteria for where it actually places it. And then I might do something like int y. And it's got to put it there, and int z, and it'll put it somewhere. And then I might do something like boolean test, something along those lines. Equals true. So whenever we write these declarations, what the compiler has to do is it has to put these somewhere in real memory on a real computer, because things aren't just magic. They have to follow some sort of actual placement. So maybe we want to mess around with some of this stuff. And a good way to do that is to be able to look at the actual places that things are at. And so the way we do that is with pointers. So what I am going to do here is I'm going to create something called a int star. And when I do star, what that means is it's a pointer. And we'll get into some examples in a little bit, maybe next time, depends on if we have time. So I'm going to create an integer pointer called pointer. So whenever you want a pointer, you just give the data type of the kind of pointer that you want it to point to, and then a star to specify that it is a pointer. And the data type will determine what it's actually allowed to look at. So if I have an integer pointer, I should make it point to something like x or y or z, but not something like test. And part of that is because of the fact that, like I said earlier, these things are going to have different sizes. So an integer is going to be bigger than a boolean. So it wouldn't really make a whole lot of sense for me to have an integer pointer look at a boolean pointer, because then I really don't know how to interpret the data. So I'm being a little bit misleading with this diagram for the sake of simplicity. These integers here are actually going to be bigger than this one. In fact, they'll take up 4 memory spaces in reality. But I digress. The idea is that we can point at these things. So if I wanted to do something like this, where I said pointer equals 0, and then I see out. And so the way I access the contents of a pointer is also with a star. I'm going to say star pointer and line. And let's just, for the sake of this, let's assign these some values too. In fact, let me make them different colors. Right, so let's say this one, int x equals 3. Let's say 3, and then we might have y equals 7. So put 7 in there, and then I will do z equals 5. Okay, so we might have memory that looks something like that. Now these actual addresses, they might not go in a straight line like that. That only really happens under specific circumstances, and we might talk about that a little bit. So if I did something like int pointer equals 0, what that's going to do, and the kind of strange thing is that this is going to allocate some memory here, and it also needs to put pointer somewhere, so will say, I'm going to create a variable 0. And what this does is, because it's a pointer, it allows me to look at locations. So what pointer is going to do is it's going to be able to go up here, and it's going to point to that. And so whenever I use pointer, it should tell me the contents of that space. So if I said pointer equals 0, and then see out pointer and line, this would print, I guess we don't really have a whole lot of space, this would print 3. And the reason that is because it's pointing to the location 0, which is the one I explicitly gave it, and the contents of that location is 3. Hopefully that makes sense so far. What if I did pointer equals 1? Oops, don't want to do that. What do you think pointer equals 1 is going to print if I did that one instead? 7, right? Exactly. Got it. So now if I do pointer equals 1, it's going to point to this location. Whenever I access it, it's going to print 7. So if I wanted it to print 5, I'd have to set it equal to 2, right? So for the sake of example, we'll leave that there. Now what happens, let's just say, so I'm not actually checking what the contents of any address is. What if I did pointer equals 3? What do you think is going to happen? So actually, let me change this a little bit. Choose there. Yeah, it's going to print some junk. So the reason that is has to do with the fact that this is a Boolean, and we're accessing data that's at a Boolean and not an integer. So I know I'm writing here just pointer equals a number. That's not what you typically do in practice. We typically actually base it off of variables. But yeah, if I try to access data that doesn't actually make sense as an integer, I'm just going to get random garbage. And that's partially because if you remember from CPE 100, did they go over? I don't think they go over IEEE actually in that class. But let's just say, you're probably familiar with like signed integers, which have like 2's complement, the 1 in front, and they flip the bits, right? And then there's also just a normal integer where it's unsigned and we just read it straight up. So if I was to look at an integer and an unsigned integer with the same pointer in the same memory location, those two different things mean completely different values depending on how you interpret them. So if I, was to look at a value that was, let's just say for the sake of the example, was like 1101, we'll just say 4 bits for the sake of simplicity, then if I interpret that as a normal integer, this is 0, 1, 2, 4. I assume everybody's taken CPE 100, right? Hopefully. I don't know if that's a prereq for this class, but well, hopefully you understand a little bit of binary. Oh, no, I'm not even counting right. Apparently I don't understand binary. That's a problem. Yeah, right? These are powers of 2. So this is 2 to the 0th, 2 to the 1st, 2 to the 2nd, 2 to the 3rd. So this is 1 plus 4 plus 8, which is 13, if I interpret it normally. But recall that there's also the 2's complement, where if I want to add a sign to an integer, that's a way to represent it. So in that case, if you remember, this was the sign bit, and then we flip everything else and add 1. So in reality, this is 0, 1, 0. I guess I would have actually subtracted 1 first, because of the 2's complement. So this would have been 1, 0, 0, and then so this is minus 1, and then I flip the bits, which is 0, 1, 1, which this is 1 plus 2 is 3. So this is, and if you don't remember the conversion, that's totally okay. This is mostly just for the sake of an example. This is 2's complement. And these are two radically different interpretations of the same binary. But, realistically, I'm just storing everything as binary on the computer. So the way I interpret it is very important. And the way that you will tell the computer to interpret it a specific way is by using that data type in front of a pointer. So if I looked at that data with an integer pointer versus an unsigned integer pointer, it gives me very, very different results when I try to actually look at what's going on there. Any questions on any of this so far? I'll probably get back to the actual programming now and how we can use this stuff. Let's create a new project. Close out. We'll just call it pointers with a Z because we're cool. Yeah, that's fine, whatever. We'll start there. Okay, so let's see how we can actually use these in practice. So no additional libraries are needed for this, and you might have actually seen pointers before because we've been writing something like this typically, right, for our command line arguments. And we have a character pointer for argument v. So that's kind of double layered. The character pointer part comes from the fact that it's a string. So a string is really a pointer to a series of characters. That's how we actually interpret it. That's what it really is. And then it's a pointer to a pointer of characters. So this is an address. Okay. And I guess if you haven't heard the term before, address refers to the actual place in memory that things are at, just to clarify. So if I went back to that diagram, just really quick, 0 is an address, 1 is an address, 2 is an address, 3 is an address. So the address of X is 0. The address of Y is 1. The address of Z is 2. And we'll get into how to actually get those. Okay. So if I was to write similar code here, int X equals 5, int Y equals 3, int Z equals 7, and then I wanted to print X. What I might do is say something like, so now the addresses I can't really know. I knew where they were in that diagram, but as far as where the computer actually puts them, it's a mystery. So it could be anywhere. So what we want to usually do is just base this off of the variable itself. So set the pointer to point to X. So you'll see I'm putting an ampersand in front of it, and you've used that before when doing things by reference, and that's because a pointer and a reference are really just the same thing. So you'll commonly see those two words used to refer to the same exact type of thing. A reference is an example of a pointer. So that's why we didn't have to make a copy when we went and did something by reference, but we did have to make a copy when we did something by value. Just because by definition, by value, it makes a copy of it. But when I do pass by reference, it will just pass a pointer to it, which means that it has the direct address of the thing that I want to actually access. And that's why any sort of changes to it will reflect back on the actual thing when I finish. And you'll see that I can do stuff like that here in a second with pointers. So I'm going to create a pointer called integer pointer, and I'm going to make it point to the address of X. So what the ampersand does is it just gets the address of whatever variable it is that you're using. So wherever the compiler is actually putting this in memory, I'm going to get it, and maybe we'll see what it actually is here. So if I did cout pointer and line, again we'll use the star to dereference it. So include, I already have IOStream using namespace standard. Let's just throw that out. This one should print what? What do you think this will print? Seems like everybody's got the idea on that one. So this should print 5, and when we run it, we should hopefully see that. And if we don't, we should be a little bit worried. Yep, a little bit small, but you can see it does print 5. So that prints 5, which kind of makes sense. So we set it to point to X, and then we ask it with the star to dereference, or in other words, look at the contents of the pointer, which is 5. Okay, so if I did this then, what do you think this one prints? hopefully, yep, I'm at least seeing one answer. This one should print 3, right? Because we're going to point to y and then print the contents of y. So again, we get 3. So this one prints 3. Now, let's get a little bit fancy here. Let's go ahead and say we're going to see out the pointer itself and then the value of the pointer. So I'm going to maybe add some things here. So pointer equals, and then I will say the contents of pointer equals this. Alright, so let's see what happens when we run this one. So we should still get 3 for the contents, right? We haven't changed that. So we're pointing to y now. It's going to print the contents of y, and then it's going to print the pointer itself. And you should see we'll get something really strange looking. We end up getting this whole mess. Maybe I should put a space to make that a little bit easier to see. I do wish there was a way... Ah, there we go. Hopefully that's a little bit easier to see now. That's better. Okay. Yeah, so you see, it gives me the pointer, which is an address. So this could be anything. You'll see here it was a 013FCA0C, and if I rerun it, it should be something different, probably. Yeah, so completely different number. So yeah, every time I run it, different number, right? This goes back to what I was saying, you have no idea where it's going to put these things. So I can't really just know some constant number where it's going to always be. It might depend on what the operating system's doing and where it lets you actually assign your memory, or if, you know, maybe you have some sort of variable kind of running where you allocate some variables different than other variables, then we expect that to be a different place. But the general idea is that this is going to refer to a location, and this refers to the contents of that location. And it's okay if you don't really understand why this looks like this. There's an A in there, that's not a number. This is hexadecimal. If you haven't learned that in the past, that's okay. Just know it's a place, and an address is a location to where things live. So, yeah, that should be the place that it is in memory. That's the name of the place that it lives, rather. So let's just do a few more things with this. So first things first, let's do some things with the addresses. So if I do this for all 3 of the variables that I had before, x, y, z, and I print their addresses, do you think there's going to be anything special about when I print these? So the memory locations, they're going to print the addresses of those variables, right? Is there anything special about those addresses that you expect to happen with these? And you guys are right, it is going to be the memory. It's going to be sequential? Not necessarily. And that's not because of the way memory... Well, it could be a little bit because of the way memory is allocated, but it also might have to do with the fact that these aren't actually necessarily executed sequential. I know that might seem crazy, but x equals 3, 5, 3, 7, these might not actually get executed in that order, which seems counterintuitive, and it kind of is, but it has to do with the way the compiler optimizes things. So it might not be sequential. But what about this? What about that pointer? Do you expect it to be the same or different from all 3 of those? Or bigger or smaller? Or is there some sort of relationship between the pointer and any of the addresses I'm going to print? Yeah, you got it. Exactly. It's going to be the same as y. At least it should be. And they will be the same size too, yep. But you'll notice that I should probably put some spaces. Yeah, so if we look at y, that address is the same one as this one. Which makes sense because this pointer is pointing to y. We set the pointer to point to y, so we expect its address to be exactly the same. Let me put some spaces here to make that a little bit easier to read. Okay, cool. So we can verify that when we get an address, it's going to be the same as the other address that we actually got it from. So the address of y didn't really change. It's kind of like statically allocated, right? It's just in one place. So let's do some other stuff here. What if I said y plus equals 2? Let's say 12. Make it a little bit bigger. Do you think anything's going to change now? Well, let's find out. No, nothing's going to change? All right, let's see. Ah, it printed 15. And the address has changed, but we expect that, right? Because we said it just kind of randomly allocates it. So I affected y, but the pointer, like, that updated too, right? I never did anything to the pointer. Why is it updating? We'll consider, and this goes back to that whole pass by reference thing. What happens? So I again have something similar here where I have an integer pointer. This pointer we'll say is pointing to something better. Let's update this to look like our code. So let's say we wrote the same exact code here. Apologize for my ampersand, it doesn't look very good. But let's say I have pointer set to equal the address of y. And then I do y plus equals 12. What this is going to do, right, is it's going to look at y and it's going to say, I need to make that 12 bigger. So it's going to go to y, which is in memory location 1. So the compiler also knows it has pointers to all of these variables. It knows exactly where they are. And it says, well, y, that's going to become 12 bigger. I'm going to set y to equal to 19. And now, when I go to see out the pointer, consider that this isn't a copy. It's actually just a thing pointing to that location, right? So it's going to go here and it's going to say, well, I need to figure out what's at that memory location. And it's 19. So the fact that I set it before I modify it doesn't actually do anything because of the fact that it reads from that location rather than actually making a copy like we normally would think to do with variables. So anything that happens to the place that it's pointing at is going to get reflected whenever I go to interpret that same thing. Does that make sense? So pointer looks at a location. So any values that change will end up changing. And that's exactly what pass by reference has been this whole time. They pass you a pointer, so when you go back up to the main, or wherever you called it from, it's going to reflect any of those changes because it was looking at the location of the thing, and any changes that it did changed the same location. And so that's why pass by reference works. Okay, so maybe we'll do one or two more things with pointers, and then we'll come back to it in a little bit here, and we'll do some more stuff next week. Right, so another way I might be able to do this is by... So let me start making some more variables here. Let's make pointer x and pointer y, and I'll set pointer y equal to that. Pointer y equals pointer y. Contents of pointer y is this. Right. And so I will also set a pointer x equal to x. And so if I did something like x plus equals 4, hopefully we now understand it will actually update the value of the pointer to x as well. Let me delete this because it's not true anymore. Let me actually create another pointer as well. Not for z, but we'll just call it pointer extra. I'll use that in a second. So let's say I wanted to update x without actually having x. Well, what I can do is, so in the same way that we've been dereferencing these previously, again, looking at the contents of it, by putting a star in front of it, we can do the same thing with an assignment. So I could say pointer x equals 10. And let's just throw more stuff in here. So let's say x equals x say y and z. So we'll print all the addresses and the contents of the addresses along with it. Oh, I didn't actually put that there. I guess that's why I had it. Okay. So now, let's take a look at this. So we created a pointer that points to x. We created a pointer that points to y. This one points to y. This one points to x. So now I'm taking the address, or rather, not the address, but the value of the pointer that points to x and setting it equal to 10. So what do you think x, y, and z are going to be in this case? $10, $15, $7. Fair. Any other guesses? Alright, let's run it. And you should see that you are right. Hopefully. There we go. So yeah. 10, 15, 7. And then you'll notice that the contents of pointer y is also 15, and the contents of pointer x is 10. So, and again, that these match. So pointer y is the same address as y, and pointer x is the same address as x. So I can also, whereas I access the variable and change its contents, I can also change the contents via the pointer, and it will reflect in the variable. So you'll see x updated here without me ever actually really using the variable x, because I have the address that it's at, so if I modify the contents of that address, it will change. So I feel like there's one extra thing I wanted to do here. Ah, yes, I know. So let's say I do pointer extra equals pointer x. And I say pointer extra plus equals 4. Let's make sure you put a star there. Now it's going to get printed. Or is anything going to change, or is there just nothing is going to happen, I guess? So it's still 10, 15, 7. Well, x change. Good question. Let's find out. So if nothing changed, it should be 10 again. But it's 14. So yeah, you're right. X will change. And the reason is pointer X and pointer extra are pointing to the same location. So I can set as many pointers as I want to look at a location, and they'll still all be referring to that same location. So any change I do to them will reflect the same variable. So when I did pointer X, just to explain what's going on in case you haven't noticed, I set the contents of X to be 10 based off the pointer, and then pointer extra is also pointing to pointer X, right? So I can add 4 more to X because it's pointing to X. And I guess we are at 11:15. So I'll let you think about that. If you have questions, let me know. But if you have to go, by all means, go. I will post this probably later on Canvas. So if I have, for example, 25 pointers to X, if I change one, it will change all of them. Right, or at least the contents. It won't change the pointer itself because the pointer is a static address. So if I was to go back to this image, so if I had like pointer 1, pointer 2, pointer 3, pointer 4, and they all equal the address of X, they're all going to equal 0. But if I do any sort of change to it, it will reflect in the memory location rather than the pointer itself. So the idea is that whenever I use this dereference operator, star on a pointer, it says, go get the stuff at that location. So it will figure out where it's pointing to, and then based off of the data type, it will interpret all of the binary there as an integer or a boolean or whatever. So if I have them all pointing to the same location, any changes that happen will get reflected whenever they try to interpret it, because they're all looking at the same data and they're all interpreting it the same way. As an integer or whatever. There's that. Is there anything new we need to know for assignment 3? Or yeah, you should be good as of today. It's on inheritance, so you really just need to be able to inherit from the player and the weapon class, and I would say I don't think it uses any static variables. I haven't looked at it too much, honestly, but it is just inheritance, so you'll basically just need to create a player class, an item class, and then 3 inherited item classes, 3 enemy inherited classes, and just remember to put the word public, I guess. And there's skeleton code, so I'm sure quite a bit of it is already written. Okay, so on that note, I'll stick around for questions while I close this up, but if you have to go, by all means go.